This one. So in air, the primary factor is temperature. If I was dealing with water, water gets a little more complicated because although temperature is a big one, you also have salinity, how much stuff is in the water, salt and stuff. You have pressure. What is the pressure of that? And a number of other things. This is what's called the sonar equation. When I was in college, being an oceanography major, we deal with the ocean, and one of our primary tools in oceanography is sonar. So understanding how sound propagates through water is very important for an oceanographer. So I actually took a physics course just on how sound moves through water on that. But we're going to deal with sound in air, and it's temperature. Temperature is the value we worry about. And basically, as the speed changes, will change about 0.6 meters per second with every change of 1 degree. That means it's going to go up. As temperature goes up, the speed of sound goes up. As temperature goes down, the speed of sound goes down. And so the speed of sound, S of S, is going to equal 331 meters per second plus 0.6 T, where T is temperature in degrees Celsius. So the temperature here is in degrees Celsius. The higher the temperature. Now, if I had a higher temperature, why would our molecules be able to move faster and pass on their energy faster? Pardon? Well, yeah, well, I mean, why does raising temperature make them go faster? More energy, right? Well, what is temperature? Temperature is a measure of what? The average kinetic energy. What is it that changes? Is the mass or the velocity change? Velocity. So more kinetic energy, more velocity. Remember, this is our raise. We raise the kinetic energy. In other words, they're moving faster. Like in the air, that molecule is now moving faster. It can go from here to over here faster, so it can transfer that energy onto the next molecule faster because it's moving faster. Moving faster. Works the same way in steel. Works the same way in water. But it's also the speed of sound. You know, underwater, can you hear sounds underwater? Yeah. Can you tell direction underwater? And there's a reason for that. Your brain is an awesome computer. If I hear Zach talk, I know Zach is over here because this ear receives the sound just a little bit before this ear. And although on a conscious level, you do not hear that difference, your brain gets the signals at slightly different intervals. Remember that your nerves are electricity, so they're moving near the speed of light. That signal is moving near the speed of light. So the signal is coming at different times, and so your brain can calculate, oh, that sound came from that direction, and things like that. But underwater, the sound, because the sound is moving so much faster, right? It's moving basically almost 5 times faster. That difference is so small, your brain says, oh, that's right in front of me. Or it could be right behind you. But basically, your brain usually interprets right in front of you, uses other things. So all sound underwater feels like it's coming from in front of you or right behind you rather than off to the sides and things like that. Yes? Not with sound. Because like I said, because it's going to come in at the same time. Now, you may be aware that someone's over here, so you go, oh, the guy's over there, that's where the sound's coming from. But a lot of times if you don't know, like in diving, to signal your dive buddy, if you kind of lose track of them, or to get their attention, if they're not looking at you, you just you bang, take your dive knife and you bang on your tank, and that way you look around, it's like, I hear the noise, and you look around and find out where they are. Things like that. But you really can't tell, you can't say, oh, he was over there. Dolphins can do that, but we can't. The dolphins live in the water. Questions? In a little bit, you're going to be doing a lab, another day, doing a lab about finding the speed of sound. Loudness. Loudness. How loud things are. First of all, we need to talk about intensity. Intensity. Intensity is the letter I. Our unit is the watt per meter squared. Watt per meter squared. Basically, it's the energy that goes to an area, space per time. In other words, if I have this piece of paper, how much energy is going through this piece of paper at a given per second on that? That's my intensity on that. Now, it is proportional to the square of the wave of the amplitude. Remember, amplitude tells us how much energy is there. But you want to note, this also follows the inverse square law. Because if I have a sound, and then when it gets to this point, it has a certain amount of intensity. But as this travels outward, this energy is doing what? I mean, as this circle gets bigger, are we adding any more energy? No. So what's happening to our amplitude as it goes out farther? Our wave gets smaller and smaller. I mean, but this follows the inverse square. So one of the factors, how much intensity, also has to do with how far you are away, right? So where you are. Obviously, if you're at the Metallica concert, it's a lot different if you're standing right in front of the stage compared to if, like, you're out in the cheap seats way in the back. There's a lot of advantage to the cheap seats in the back. Save your ears. And all that. But it does fall in this is why, explosives, they look at that. If you've ever watched Mythbusters, they have the little things they use to explode. They'll set things at different intervals. How far away would you have to be? They do a lot of survival things. How far would you have to be to survive this explosion? What they're measuring is this. They're measuring that intensity because it really is like a sound wave coming out, that intensity going on. So intensity is part of that loudness. But loudness is subjective. Loudness is based on human hearing. And even other people's hearing and what you are doing. Loudness can be very subjective, like at night. The thing, like you're at home, you notice like at home, you get up in the morning, or you get home in the afternoon. If you were watching TV last night, you'll notice when you get home, the TV seems to be really, really soft, doesn't it? Well, it's because at night, we live in a very noisy environment. Lots of noise. We live in a very noisy place. We have all this, it just kind of bombards our ears all the time, and they get tired. But at night, as things calm down, what happens to that noise level? It goes down. At night, the noise levels go down, and so you don't need to do that. Also, you're very relaxed. It's also at night, when you're asleep, you hear why do you hear those little sounds at night? Because your brain is straining to hear those sounds. It's almost like they turn the amplifier, it turns the amplifier up. So you don't necessarily have to have those sounds on as high. So especially after you've been relaxed a while, nice sound, quiet place goes down. But after a while, the sound levels go up. So that can be very subjective too. What's loud, like in the evening, may not be loud during the day, just because your ears have been desensitized over time. But we measure loudness, and we call it intensity level. This is actually our loudness. We use the symbol of a capital L, and we use the unit of the decibel. Decibel. A tenth of a bell. A tenth of a bell. And a bell is named after Alexander Graham Bell, who is most widely known for his invention of the telephone. The telephone. Although Bell invented a lot of things. Bell was actually involved very much in like the National Geographic Society. His family, the extended family, I think it was his son-in-law, was like the first president of the National Geographic Society. But also, Bell actually made a boat that held, I think, the water speed record for decades. For decades. Because Bell invented the hydrofoil, which is a boat that flies on wings. Basically, if you put wings on the bottom of a boat, it lifts the hull of the boat out and you fly on the wings. Hydrofoil. But Bell's the one who invented that. He held the water speed record, the boating speed record, for decades. I think something like, from like the turn of the century until almost like the 50s or something like that. So a very long time.